So last time we started L'Hopital's rule for limits. And so let me finish that up. So as it says, first of all, L'Hopital's rule is for limits. And so, for example, if we have this scenario where we're taking the limit of f of x over g of x as x goes to a, and we get one of two indeterminate forms, we get either 0 over 0 or infinity over infinity, then L'Hopital's rule allows us to transform the limit. It doesn't necessarily solve the limit for us, but it allows us to transform the limit. So here, rather than trying to take the limit of f of x over g of x as x goes to a, that limit, according to L'Hopital's rule, is equal to the limit of f prime of x over g prime of x as x approaches a. Is that helpful? Maybe, maybe not. It just depends on the situation. All L'Hopital's rule is telling us is that it can transform the integral in this scenario where you have 0 over 0 or infinity over infinity. Once we've transformed the integral, we're starting over again. This is a new integral problem, the limit as x approaches a of f prime over g prime. Hopefully it's easier than the original. One other comment I do want to make is here, the limit does not have to be a two-sided limit as x goes to a. It can be a one-sided limit from the right or the left, and it does not have to even be a finite limit. So that could be an infinite limit. X goes to infinity, x goes to minus infinity. The main thing we're looking for is that we have a quotient and that we get the indeterminate form, either 0 over 0 or infinity over infinity. So if we get that, then, you know, L'Hopital's rule is in play, and we can try and figure out the limit of f prime over g prime. So I did do a proof just because I wanted to motivate it somehow, you know, but you don't need to know the proof. You do need to know the result. You know, it would be good to try and really think about what is L'Hopital's rule really saying, you know, geometrically or from some point of view. I think it's pretty deep, personally, so I'm still working on it. For the notation, when we do use L'Hopital's rule in a limit problem, I mean, that's the only place we would use L'Hopital's rule. We like to write L apostrophe H when we actually do use L'Hopital's rule. So once I've applied L'Hopital's rule now here, I'm taking the limit of f prime divided by g prime as x goes to a. And one thing I will mention is here in L'Hopital's rule, we are not doing a quotient rule of f over g. It's the derivative of the numerator divided by the derivative of the denominator separately. So before I get into the examples, I want to make some remarks essentially about this thing we call infinity. So the first remark I want to make is be careful. We have forms that might look like they're indeterminate, but they're not indeterminate. So for example, 0 over infinity, you should think of 0 over infinity, which is equal to 0, by the way. You should think of this as 0 times 1 over infinity. And here, this is not really math, but this is just, you know, a way for us to think about the limits. And here, 1 over infinity is 0. So this is really the same as 0 times 0. And 0 over infinity here, it's not indeterminate. It just equals 0. So if you're doing a limit and you get your limit 0 over infinity, that just equals 0. Similarly here, infinity over 0. Again, I think the best way to think about this is to think about this as infinity times 1 over 0. And that equals, you know, 1 over 0 in a limit is some type of infinity, plus or minus. So here, this is actually infinity times infinity. So here, infinity over 0 is not indeterminate. If you get infinity over infinity in a limit, that's going to equal, you know, plus or minus infinity, depending on what the sign, what's going on with the signs. So yeah, similarly, infinity to the infinity is equal to infinity. It's not indeterminate. 0 to the infinity, this is just equal to 0. Infinity plus infinity, this is just equal to infinity. And 1 to the infinity, which I'll talk about somewhere at the bottom of this, that's just equal to 1. You know, we want to compare with our indeterminate forms. For example, infinity raised to the 0, that's an indeterminate form. Because when you raise something to 0, it's usually 1, but starting with infinity, I don't know what happens. Here's 0 raised to 0. That's an indeterminate form. Usually, when you raise something to 0, it's 1. Here, the base is 0. Here, the way I like to write it is, I don't like to write it as 1 to the infinity, and I'll mention something about this. I like to refer to it as the 1 to the infinity type. And I'll talk about this in 1 second. And then infinity minus infinity. That's an indeterminate form. The other one I didn't mention, there's not one on this list that's similar to 0 times infinity, and 0 over 0 and infinity over. So these are our 7 indeterminate forms, but sometimes, you'll get these other forms that look indeterminate, but they're not. So watch out for these ones. These are not indeterminate. Okay, so the other thing I wanted to mention is this symbol that we use for infinity. It's really important to remember that infinity is not a number. It's a behavior. It's the behavior of getting larger and larger without any kind of bound, forever getting larger for, plus infinity. But, it's a bit misleading because we have one notation for this idea of infinity, but there are many different ways to get to infinity. That is to say, there's a hierarchy of infinities. There's more than one concept of infinity. It's weird. So for example, if you look at these 3 functions, the exponential function, y equal to x. So the exponential function right here, y equal to x, and y equal to ln of x. If we take the limit, we can see the limit of all 3 functions goes to infinity. But they all do so in a drastically different way. Even though I say the limit for all of these 3 functions is equal to infinity, the behavior, how it goes to infinity in each of these 3 cases is very different. And here we can think of this as 3 different ways to get to infinity, 3 different types of infinities, 3 different, examples of infinity behavior. So the exponential function goes to infinity the fastest. Polynomial functions are kind of, the next level of functions that go to infinity, and then the natural logarithmic functions go to infinity the slowest. And so because of these different rates of approaching infinity, that's why we have indeterminate forms. That's why infinity over infinity, we're not sure what that means. Is the infinity on top going faster than the infinity on the bottom? Are they going at the same rate? Is the one on the bottom going faster? So here's a comment about 1 to the infinity. And the only reason I make a comment about this is because the book is very loose with this notation. So 1 to the infinity, what does that mean? That really doesn't mean anything. What that means is the limit of 1 over x as x goes to infinity. That's what 1 to the infinity would be interpreted as. And well, 1 to the x for each fixed x is just the number 1. So this limit as x goes to infinity of 1 to the x is just 1, or 1 to the infinity equals 1. So now compare it with this other situation. Here I have the limit as x goes to infinity. Now look at the base here. It's 1 plus 1 over x, all raised to x. So when we send x to infinity, this exponent here, that goes to infinity, okay? But look what happens to the base. The base is not equal to 1, it's going to 1. If the base were equal to 1, there would be no problem. The limit would be 1 to infinity and it would just equal 1. But here the issue is, here the issue exactly is it's going to 1. It's not equal to 1. And for example, if you take a number larger than 1, like 1.1 or 1.2 or 2, and raise it to infinity, that's going to blow up to infinity. If you take a number between -1 and 1, like 0.9, 0.8, raise that to infinity, that's going to go to 0. So here the issue exactly is that we don't have 1. If we had 1, if it was 1 to the infinity, no problem, that equals 1. Here we have what I call, and I apologize for that, we have what I call a 1 to the infinity type, and it's an indeterminate form. The book just refers to it as 1 to the infinity, which I feel is really misleading because 1 to the infinity is not indeterminate. So I like to call it a 1 to the infinity type. And the point exactly is that the base here doesn't equal 1. If it were 1, there wouldn't be any issue. The point is it's going to 1, and the exponent is going to infinity. And so now the question is, there's sort of this race between these two limits. Which limit gets where first? What happens? Do they balance out? Does one get to where it's going first? So that's why the 1 to the infinity type is an indeterminate form, but 1 to the infinity is not indeterminate. Okay, so let's start doing some examples. So for L'Hopital's rule, it's a limit problem. And when you try to apply the limit, if you get 0 over 0, then we can try L'Hopital's rule immediately. So what does that mean? I'm going to take the derivative of the numerator. So here, derivative of sine is cosine. And then divide that by the derivative of the denominator, derivative of x is 1. And then now take the limit. And so now we reset. This is a new limit problem. How do we, the first thing to try with the limit problem is plug it in. So here I plug in a 0 for cosine. Cosine 0 is 1. I'm done. I can conclude limit of sine of x over x equals 1. And we knew that, but we know it again now using a L'Hopital's rule. So here we have limit as x goes to infinity, natural log of x over x. Remember that when you're doing limits involving e to the x, natural log of x, it's really helpful to have the graph and to think about the graph. And here you can see the numerator as x goes to infinity. And the denominator goes to infinity. So I have an infinity over infinity type indeterminate form. I can just immediately do L'Hopital's rule. And here I'm expecting the answer to be 0. Why? Well, I suspect that x goes to infinity faster than ln of x, based on the geometry. That suspicion isn't enough. This is math. We need solid proof. So let me actually do the limit. I try the limit. I get infinity over infinity. I do L'Hopital's rule, which means I take the derivative ln of x, which is 1 over x, and divide that by the derivative of x, which is just 1. So here, this limit is just 1 over x divided by 1 is just 1 over x. And now we send x to infinity. So if you send x to infinity, 1 over x goes to 0. So now we take the limit, send x to infinity, 1 over infinity is 0. I could conclude that my limit of ln of x over x is x goes to infinity equals 0. So that's the original limit that we started with. So I can now conclude it equals 0, by this L'Hopital's rule technique. One more, slightly more complicated. So limit of e to the x minus 1 over x squared. Again, it's really helpful to remember your exponential graph for the limit here. So e to the x goes to infinity. The minus 1 is not going to affect it. So certainly e to the x minus 1 goes to infinity. X squared goes to infinity. So this is another infinity over infinity type indeterminate form, and I can use L'Hopital's rule. Here, I expect this answer to be infinity. Why? Because exponential functions are the fastest growing functions. They certainly will grow faster to infinity than a polynomial. Again, my gut feeling is not enough. So here I do the limit. When I do the limit the first time, numerator goes to infinity, denominator goes to infinity. I have infinity over infinity, so I apply L'Hopital's rule. The derivative of e to the x minus 1 is the derivative of e to the x, which is e to the x, minus the derivative of 1, which is just 0. So here the derivative of numerator is just e to the x. The derivative of the denominator using power rule is just 2x. So now I try the limit of e to the x over 2x as x goes to infinity. Well, here we get another indeterminate form. We get 0 over 0 again. No problem, just apply L'Hopital's rule again. So here you see I take the derivative of the numerator. The derivative of e to the x is just e to the x. The derivative of 2x is just 2. And now try the limit again. So basically the procedure is when you get to an indeterminate form, or at least after you've applied L'Hopital's rule, you can do any simple algebraic simplifications if there are any, and then try the limit again. So here I try the limit, and now we see that the numerator blows up to infinity, the denominator is constant, so the limit is infinity. So here you see two examples of, even though they're both infinity over infinity, In one case, the limit goes to 0. In the other case, the limit goes to infinity. This is exactly why this is an indeterminate form. You see, we have the sort of, depending on how it's going to infinity, the limit will behave one way or the other. Okay, so now we start to do slightly more complicated problems. So here, the 0 times infinity type indeterminate form. Why is it indeterminate? So by the way, 0 over 0 is indeterminate because dividing by 0, we don't quite know what's up with that. And usually if you have a 0 in the numerator, the whole thing is 0. So that's confusing. And infinity over infinity, again, usually when we divide by infinity, it goes to 0, but I have an infinity in the numerator. So is it blowing up? Is it going to 0? We don't know what's going on. Here, when you have 0 times infinity, usually 0 times a finite number always equals 0. But infinity is not a finite number. So what's going on here? Is it equal to 0? Is it equal to infinity? Does the universe blow up? What's going on? So the trick is to rewrite the product as a quotient. Why? Because L'Hopital's rule works only on quotients, right? It's limit of f over g. So here I'm going to take the product, rewrite it as a quotient. Now review your algebra here. Here, if we multiply top and bottom by b, we get back to the original a times b. I haven't changed what it is, I've just changed what it looks like. So I'm going to try and rewrite it as a quotient and then see if we can do L'Hopital's rule. So here's a limit. X goes to infinity. We do this piece by piece. First you should recognize this is a product. So here the first term in the product goes to infinity. For e to the 1 over x minus 1, do it piece by piece. So remember here, I have e to the 1 over x. As x goes to infinity, 1 over x goes to 0. So this will go to e to the 0, which equals 1. But I have a minus 1 hanging around outside there. So this entire limit, as x goes to 0, this entire thing will go to 1 minus 1 or 0. So this will be an infinity times 0 type of indeterminate form. And once I see in a limit infinity times 0, I go, aha, I've memorized the strategy for what to do in a limit when we get this indeterminate form. I'm going to divide one of the terms by the reciprocal of the other. So here what I'm going to do is I'm going to divide e to the 1 over x minus 1 by the reciprocal of x. The reciprocal of x is 1 over x, and I'm dividing by 1 over x. If you look, we haven't really changed anything. If I multiply top and bottom by x, in the denominator, you just get 1, and in the numerator, you get back. This takes us back to where we started from, which isn't helpful, but I just want to show you we haven't changed anything, just what it looks like. But look now what happens when we try to apply the limit. In the numerator, 1 over infinity is 0, e to the 0 is 1, 1 minus 1 is 0, numerator goes to 0. In the denominator, I have 1 over infinity, denominator goes to 0. So I have 0 over 0, so we can use L'Hopital's rule. So I take the derivative of the numerator. Now be careful. For e to the 1 over x, we need a chain rule. So right here, I need a derivative of the outside. The outside function is the exponential function. Remember, the derivative of e to the x is just e to the x. So here, the derivative of the outside evaluated at the inside is just e to the 1 over x. Times the inside function is 1 over x, which we should think of as x to the minus 1. And the derivative of x to the minus 1, you bring down the minus 1, subtract 1 from the numerator, is minus x to the minus 2 or minus 1 over x squared. That's the derivative of the inside. And in the denominator, we just have 1 over x here. And so again, that's x to the minus 1. So the derivative there is minus 1 over x squared. And so now we can do, we can do some cancellations. I can cancel this minus 1 over x squared in the numerator and the minus 1 over x squared in the denominator. That just leaves us with e to the 1 over x, limit as x goes to infinity. And now we can, try to take the limit. As x goes to infinity, 1 over x goes to 1 over infinity, which is 0, and e to the 0 is 1. So here I should have concluded here. My final answer is that this limit as x goes to infinity of x times e raised to the 1 over x minus 1 is 1. That should have been, my final answer here. So, conclusion from down here. Yeah, so here, once I identify the indeterminate form, we have to have the strategies memorized and the indeterminate forms. And, so that's kind of how the game goes. So here, it's a limit problem. Let me just try and take the limit. As x goes to infinity, I know this term in the front, that goes to infinity. No problem. As x goes to infinity, take a look at this natural log of 1 plus 2 over x. 2 over x will go to 0. So this entire term will go to ln of 1 plus 0, or just ln of 1. And you remember ln of 1 is 0. So here I have an infinity times 0 type indeterminate form. And so now I've memorized, in this case, I'm going to divide one term by the reciprocal of the other. So here's the thing. Typically, we're going to divide by the simpler function. Like, yeah, I could divide by x, or technically, I could divide by 1 over x, or technically speaking, I could divide by 1 over ln of 1 plus 2 over x. But if I divide by 1 over ln of 1 plus 2 over x, that's a mess. That taking the derivative of that is a real mess. I would much rather divide by 1 over x, because that's easier to differentiate. So I take the reciprocal of x, which is 1 over x, and divide by the reciprocal. And here, you remember, if you multiply top and bottom by x, you'll get back to where you started. Theoretically, we could look at x over 1 over, already it's a mess, ln of 1 plus 2 over x. And when you try to do L'Hopital's rule, we would be trying to take the derivative of this denominator term, by itself, this numerator term, and this is ln of 1 plus 2 over x, the whole thing to a minus 1. So we need this chain rule. So it just gets, messier and messier. So divide by 1 over x, apply the limit. This time you get 0 over 0. The numerator goes to ln of 1. Denominator goes to 1 over infinity. And so that's 0 over 0. So derivative of the numerator, now be careful here, I need a chain rule. ln of 1 plus 2 over x, that's a composition. The outside function is ln, the inside function is 1 plus 2 over x. So remember, the derivative of ln of x is just 1 over x. So here the derivative of the ln evaluated at the inside would be 1 over 1 plus 2 over x. The inside function is 1 plus 2 over x. This part right here is the inside function. And remember, 2 over x is just the same as 2 times x to the minus 1. So the derivative here is 0 plus 2 times negative x to the minus 2, or negative 2 over x squared. And so that's the derivative of the inside right there. In the denominator, 1 over x is just x to the minus 1. Derivative of x to the minus 1 is minus x to the minus 2, or minus 1 over x squared. And now we can do some algebra. Here, negative 2 over x squared, that's the same as 2 times negative 1 over x squared. And there's a negative 1 over x squared in the denominator. So I can cancel the negative 1 over x squared. And the 2 survives. And then the 2 multiplies to the 1 over 1 plus 2 over x. We get the limit as x goes to infinity of 2 over 1 plus 2 over x. And now we can take this limit as x goes to infinity. The 2 over x goes to 0. So we get 2 over 1, 2 over 1 plus 0, or just 2. So yeah, they're a little bit drawn out. There's, kind of a bunch of steps. But once you know the strategy, then you're kind of grinding it out, you know, and knowing the indeterminate forms, which I'll list all at the end, and knowing the strategies that go with them is really important. And I'll list all of those together at the end as well. So this next class, so we had 0 over 0, infinity over infinity. So that's 2 indeterminate forms. Then we had 0 times infinity. So that's a third indeterminate form. Now we get 3 more. Infinity raised to the 0, 0 raised to the 0, and a 1 to the infinity type. The book calls it 1 to the infinity, but that's misleading. So here's 3 more. So this gives us 6 indeterminate forms. The last indeterminate form will be infinity minus infinity. So these 3 indeterminate forms are the most complicated. The strategy is to rewrite, use the fact that A equals e to the ln of A, and then use the continuity. And this slide might look slightly different from the slide I sent you. I modified that just a little bit. So here, you know, the idea is to try and bring the natural log into the picture. If I can bring the natural log into the picture, maybe we can use properties of the log and address these terms that are in the exponent. Because these indeterminate forms all have one thing in common. They have an exponent. Infinity raised to the 0, 0 raised to the 0, a 1 to the infinity type. So perhaps the natural log can help us simplify it. Okay, so let's try a problem. So here I have a limit of x raised to the 1 over x as x goes to infinity. First, just get used to this, what we're looking at here. This is the variable x raised to a function of x, which is 1 over x. You know, another way to think about this is the xth root of x. I don't know. What does that even mean? So let's try the limit. The base here, when you send x to infinity, the base goes to infinity. 1 over x goes to 1 over infinity. So the limit here is infinity raised to the 1 over infinity, or infinity raised to the 0. That's one of our indeterminate forms. So now I've memorized the strategy. Let me use the exponential function and continuity. So what do I mean by continuity? You know, I mentioned here and use continuity. So this is what I mean specifically. That continuity says that the limit of f of x as x approaches a, if we're dealing with a continuous function, is f of a. I really think it helps to think of a itself as a limit. A itself is the limit of x as x approaches a. So to me, continuity really says you can take the limit and bring it inside the function. You see here, the limit is inside the function. So in particular, if the function we're dealing with is e to the x, and we apply this continuity property, then that looks like this, that the limit as x approaches a of e to the x equals e to the limit of x as x approaches a. So look, the limit went up. Okay, so that's what I mean by continuity. So let me put it all together. So first, let me rewrite x to the 1 over x as e to the ln of x raised to the 1 over x, and then bring this 1 over x down in front. We get 1 over x times ln of x, when you bring that 1 over x down in front, and if you multiply 1 over x and ln of x, you get ln of x over x. Okay, so now let me put it all together with the continuity. So from the beginning, the limit of x to the 1 over x, x goes to infinity, is infinity to the 0. Rewrite that as e to the ln of x raised to the 1 over x. And then very important, use properties of the log to bring down that 1 over x. So now I have limit as x goes to infinity of e raised to 1 over x times ln of x, or e raised to ln of x over x. So now here's where I use the continuity. The limit only cares about the x variable, so I can move the limit up using continuity to the exponent, the only place where we have x variables happening. And now I'm going to solve this limit like it's its own problem. And I'm just going to keep it up in the exponential position. So here, when we try to send x to infinity, ln of x goes to infinity, x goes to infinity. This is an infinity over infinity type indeterminate form, which means we can use L'Hopital's rule. Be careful, I'm only using L'Hopital's rule up here for this limit in the exponent. Derivative of the numerator is 1 over x. Derivative of the denominator is 1. Now we take the limit as x goes to infinity. Here, 1 over x goes to 0. So here I have, that's in the exponent, right? The limit here in the exponent is going to 0. So my final answer here is e to the 0, or 1. And so there's my final answer. It's, once you recognize the indeterminate form, you have to know the strategy. That's really important. Here for x raised to the x, as x goes to 0 from the right. So first, try and apply the limit. The base goes to 0. The exponent goes to 0. This is one of our indeterminate forms. So now I want to use the exponential. So here it is from the beginning. Try to take the limit. I get 0 raised to the 0. No problem. Let me rewrite that as e raised to the ln of x raised to the x. This little x I can bring down in front. And so that's what I do right here. And now the limit only cares about the x variable. The only place we have x variables are up here. So using continuity, so I wrote a little letter C here for continuity, I put the limit up. So you should notice the change of position of the limit. Now I'm working this new limit up here in the exponent like it's its own problem. I'm just going to copy the e. When I send x to 0 from the right, if you think about the graph of ln of x, here's the graph. As x goes to 0 from the right, ln of x goes to negative infinity. And the x out in front, here, this x out in front, this goes to 0. So now we see I have a 0 times infinity indeterminate form. And what's the strategy here? For a 0 times infinity, you divide one term by the reciprocal of the other. So I take the reciprocal of x, which is 1 over x, and divide ln of x by 1 over x. X is the simpler function. I could divide by 1 over ln of x. It's just more work. Now I try the limit again. In the numerator, ln goes to negative infinity as x approaches 0 from the right. In the denominator, 1 over x goes to plus infinity as x approaches 0 from the right. I have infinity over infinity. We can use L'Hopital's rule. But just in the numerator. So here the derivative of ln of x is 1 over x. The derivative of 1 over x, or x to the minus 1, is negative 1 over x squared. And now we have a fraction divided by a fraction. So the x squared actually moves up. Here we have a fraction divided by a fraction. So the x squared actually moves up. I have in the exponent there, negative x squared divided by x, when we can cancel one of the x's. And so now everything simplifies to this expression. E raised to the limit of negative x as x approaches 0 from the right. We take the limit. If the limit's easy, just plug in the 0. I get the limit is 0. Our final answer, though, is e raised to the 0 or 1. So I should have, concluded here. I should have said, oh, so I can conclude that this limit of x raised to the x as x goes to 0 from the right equals 1, based on all this work right here. So it's really important to get used to the notation, but the problems aren't that bad, especially if you can practice a little bit. And of course, knowing the indeterminate forms and knowing the strategies, that's a must. So let me do what I call a 1 to the infinity type problem. And the strategy will be very familiar. We're going to use e to the ln of a. I just want to discuss again why this is indeterminate. As I said, 1 to the infinity, there's no issue with 1 to the infinity. Here the problem is, as x goes to infinity, the base does not equal 1. It's going to 1. The exponent's going to infinity. And now there's kind of a race between these two limits. Which limit dominates? Does the base get to 1 first, and then x goes to infinity? Does x blow up? What happens? Is there some kind of weird balance? So precisely because this isn't 1 to the infinity, which would be equal to 1, but this is very close. It's a 1 to the infinity type. The base is going to 1. This is indeterminate. So that's something you should think about and convince yourself why it's indeterminate. And be careful, the book just calls this 1 to the infinity, which is not indeterminate. If this limit was just like this, the limit of 1 to the x as x goes to infinity, yeah, it's easy. This, you would just say, oh, this just equals 1, no problem. But you know, that's the issue. We don't have 1 to the infinity. We have something going to it. Anyway, as I said, the strategy will be the same. We use this, rewrite so here, 1 plus 2 over x raised to the x would be the letter A here. And we rewrite that as e to the ln of quantity 1 plus 2 over x raised to the x, like this. So you see that whole thing is up there in a ln, and that whole thing is being exponentiated. Now, the whole point of this was to use properties of the log. So I'm going to so actually, I think here, you can do it in either direction. I think I first used the continuity and brought the limit up, which is fine. So look what happened to the limit. Brought it up. And then now I'm going to use the properties of the log and bring the x down. And those steps could have been reversed. I could have brought the x down first and then used continuity and brought up the limit. Either way, we end up with an expression that looks like this. And now I reset. I'm just now working this limit up here. When I send x to infinity, the term in the front, x, this goes to infinity. This second term goes to ln of 1. So I have an infinity times 0 type indeterminate form now. And I know this strategy is to divide one term by the reciprocal of the other. So I'm going to take x, the simpler term, its reciprocal is 1 over x, and I'm going to divide ln of 1 plus 2 over x by 1 over x. Now, if you take the limit, send x to infinity, the numerator goes to ln of 1. The denominator goes to 1 over infinity. That's 0 over 0. I can use L'Hopital's rule. And now be careful. In the numerator here, I need a chain rule. It's ln composed with some function. The derivative of the ln part's right here. It's just 1 over, 1 plus 2 over x. The derivative of the inside, the derivative of 1 plus 2 over x, or 1 plus 2 times x to the minus 1, is just negative 2 over x squared. In the denominator, the derivative of 1 over x is negative 1 over x squared. Here we can cancel the minus sign and the division by the x squared. We just have the 2's left. Multiply that through, and now take the limit. Remember, this is all happening in the exponent. That's how this is different from any other problem we've done. And the 2 over x, as x goes to infinity, this part goes to 0. So you get e raised to the 2 divided by 1 plus 0, or just e squared. So that's my, final answer here, that the limit, I conclude, is e squared. It converges to e squared. So, because there's so many steps for this type of problem where you have, for the infinity to 0, 0 to the 0, or 1 to the infinity type, sometimes just a style difference. It's still the same strategy, same limit problem, but some folks like to break it up into 2 steps, where they take the natural log first, okay? So here, I'm first gonna take the natural log of the original problem. So if you look at the original problem, and you can see I've put in a natural log. And the theory is here, which you wouldn't necessarily explain if you're doing it this way, but the theory is that I can write 1 plus 2 over x to the x as e to the ln of that. And then using continuity, I can bring the limit up. And so now I first want to calculate this limit, which I've written here. And then at the end, we're going to exponentiate. So here it's all the same steps. So let's review. First, using properties of the log, bring the x down in front. So there's that x. When I take the limit, x goes to infinity. The other term goes to ln of 1, or 0. If I have an infinity times 0 indeterminate form, the trick is to divide one term by the reciprocal of the other. Usually we divide by the reciprocal of the simpler expression. So I divide the natural log of 1 plus 2 over x by 1 over x. Now if you send x to infinity, now if you apply the limit, the numerator goes to 0, goes to ln of 1. The denominator goes to 0, it goes to 1 over infinity. So I have 0 over 0, I can use L'Hopital's rule. In the numerator, be careful, it's a chain rule. Derivative of the outside times derivative of the inside. In the denominator, just use a power rule. Here then cancel, cancel. The 2 doesn't cancel. I multiply the 2 to the 1 plus 1 over 2x, I get this limit. The limit's 2. So this is where, it's easy to make a mistake here. We're not done. We found the ln of the actual limit we're looking for. So now I need to exponentiate. I need to raise everything to e. So here I'm going to raise everything to e and then get my final answer here. It's the same final answer. It's e squared, but we just did it in 2 steps. It just depends what kind of style you prefer. So if I was doing this problem, the parts I wouldn't write down would be, so let me show you, the parts I wouldn't write down would be, so I would just first note that this is an indeterminate form, and then I wouldn't write any of this stuff down. I just then immediately go to this, to take the ln, the limit of the ln. Then figure out that limit using whatever techniques. And then my final answer now then would be, so I wouldn't write any of this stuff down. So then my final answer would now then be, then just exponentiate your answer. So we're still doing the e to the ln trick, but we're just doing it in 2 steps. So here's the ln, step 1, and we do that limit, and then we e our answer at the end, step 2. It's still the same, it's just broken it up into 2. It just depends if you like that procedure or not. So in general, we can conclude that the limit of 1 plus n over x raised to the x, where n is any real number, is e to the n. And if you pick n to be 1, then we get a limit definition of e. So here we can define e now, not using an integral, but as a limit. This is typically where pre-calculus starts, and it's a bit artificial because this isn't a natural definition. Yeah, that's true. That is what e is equal to, but where did that come from? At least if we use the integral definition, I have a picture I can think about and connect it to the idea of area. So the last indeterminate form is infinity minus infinity. There are no set rules for infinity minus infinity, and we almost go back to chapter 1 and think about all of our techniques. So if we might try to combine terms, we might try to factor out a common term and cancel it. We might try to multiply by a conjugate. We might try, I don't know, a squeeze theorem, so here it's on a case-by-case basis. So here for this first problem, first take the limit. As x goes to 0 from the right, 1 over x goes to infinity. Minus, if you think about the sine of x graph, as x goes to 0 from the right, it approaches 0 from above. So this is 1 over 0 and it's positive. So this is also an infinity. So I have infinity minus infinity. That's indeterminate. In this particular case, because I have a difference of fractions, I want to combine the fractions. So I multiply the first term top and bottom by sine of x. I multiply the second term top and bottom by x and combine them. Now when I take the limit of the numerator is sine of 0 minus 0, which is 0. And the limit of the denominator here is 0 times sine of 0, or 0, just 0. So here you have 0 over 0. So I can use L'Hopital's rule. I take the derivative of the numerator, no problem. Derivative of sine of x minus x is cosine x minus 1. Derivative of the denominator, be careful. There's a product here. I need a product rule. So derivative of the first function, which is x, derivative of x is 1 times sine of x. There's my derivative of the first times the second. Plus, copy down the first function times the derivative of the second. Derivative of sine is cosine. try to apply the limit again. I tried to apply the limit again. In the numerator, I get cosine of 0 minus 1. Cosine of 0 is 1. So the numerator get 1 minus 1. In the denominator, I get sine of 0, which is 0, plus 0 times 1. So I get 0 over 0 again. No problem. Let's just try L'Hopital's rule one more time. Take L'Hopital's rule. You see in the numerator, the derivative of cosine x minus 1 is just negative sine x. In the denominator, derivative of sine x is cosine. Now be careful, derivative of x cosine x, I need a product rule. Be careful. I do the product rule. Now when I apply the limit, in the numerator, this goes to 0. The denominator goes to 1 plus 1 minus 0. So the limit is 0 over 2, or just 0. So yeah, here, based on the form, I combined the two and made it a single fraction. For this next problem, first of all, when you send x to infinity, note the first term goes to infinity, the second term goes to infinity. So this is infinity minus infinity. But because of the form, you know, and this goes back to a chapter 1 problem, because of the form, we're going to multiply by the conjugate. And, you know, that's something you might need to review because it's been a while. But we multiply by the conjugate, top and bottom. Do the algebra in the numerator. And here, if you take the limit, you get infinity over infinity. Here, you actually have two options. We could do dominance of powers. So we could just look at the limit of x squared over x, because those are the highest degree terms in the numerator and denominator, respectively. And so that cancels to x. And so the limit should be infinity. Or we could try L'Hopital's rule again. That's what I did here, just because we're studying L'Hopital's rules. I did L'Hopital's rule one more time. Took the derivative of the denominator and numerator. In the denominator, remember, root of x plus 1, that's x plus 1 to the 1/2. So when I take a derivative, I get 1/2 x plus 1 to the minus 1/2. The derivative of root of x plus 1 actually gives me a fraction. And that's where this weird 1 over 2 times root of x plus 1 comes from. Now when you send x to infinity, this term here goes to 0. And the term in the numerator blows up to infinity. So the limit is infinity. But as I said, we could have done dominance of powers at that step before, which is probably what I'm likely to do, you know, just because it's a little more efficient. Sometimes dominance of powers is more efficient than L'Hopital's rule. So here's another problem. And I'm coming to the end here, so I'm going to start wrapping these up. Here, again, this one's a little tricky. Okay, so when x goes to 1 from the right, x squared minus 1 goes to 0 from the right. ln going to the 0 from the right is negative infinity. Minus this natural log also, the x to the 5th minus 1 approaches 0 as x goes to 1. So this goes to negative infinity. So here, this is of the form negative infinity plus infinity, which is still indeterminate. It's not infinity minus infinity, it's a variation of it, but it's still indeterminate. That's the same as infinity minus infinity, type indeterminate. So yeah, so anytime natural logs are involved, we typically want to use the properties of the log. So we know that natural log of the difference I can write as the natural log of the quotient. And here now I'm going to use continuity because natural log is a continuous function. What does that mean? I can bring the limit all the way inside. That's because of continuity, because natural log is a continuous function. And now be careful here. This is x squared minus 1 over x to the 5th minus 1. Don't do a dominance of powers because the limit isn't going to infinity, it's going to 1. Here, when I try to send x to 1, I get 0 over 0. I do L'Hopital's rule again, but just inside here, to the limit that's just inside the natural log. Derivative of x squared minus 1 is 2x. Derivative of x to the 5th minus 1 is 5x to the 4th. Here you can cancel x's, or you can actually just apply the limit, because when you apply the limit, just plug in a 1, we get the limit's 2/5. The final answer here is ln of 2/5. So here's just my explanation for using continuity. It's just the usual thing. The continuity means we can bring the limit inside. So when the function is ln of x, that looks like this. That looks like we can literally just bring the limit inside. That's what continuity looks like for the natural log function. So this last one is kind of sneaky. Here, as you send x to infinity, you get infinity minus infinity. And, you know, after thinking about it, you might factor out one of the terms. So I don't think it would matter in this problem. So I factor out natural log of x. So you can see I've factored out the natural log of x, and I've divided each term by natural log of x, the thing I factored out. And so now if I try to take the limit as x goes to infinity, this part right here is an indeterminate form. This is infinity over infinity. So let me look at this limit separately here. So I'm looking at this part, which is indeterminate. So before I can take the limit, I first need to figure out what x over ln of x is doing. Since it's infinity over infinity, I can apply L'Hopital's rule, derivative numerator divided by derivative denominator. Here, algebraic simplification, the x in the denominator comes up. As x goes to infinity, now the limit of x is infinity. So I know that the limit of natural log of x over x goes to infinity, and certainly the limit of natural log of x over x minus 1 would go to infinity. Subtracting 1 is not going to be that big of a difference. So if I go back to the original limit, when I send x to infinity, this natural log x term that's in the front, that goes to infinity. And we know x over natural log of x minus 1, we know that goes to infinity. So here I have infinity times infinity, so the limit is infinity. You know, we expect infinity to be the answer because here x grows faster than ln of x. So I'm expecting the first term to be bigger, but that's not a mathematical proof, just that intuition. The math we've done here to factor out the ln of x and figure out what's the limit of this part, what's the limit of this part, put those two together, that's how we would mathematically, you know, show this limit. Finally, I do want to mention that there are indeterminate forms for which L'Hopital's rule will not work. And, you know, we might have to try something else. Like, I mean, for infinity minus infinity, we don't use L'Hopital's rule, right? Sometimes we do if it works out. Sometimes it's multiplying by the conjugate. You know, here, when we try to apply the limit, so look at this function, x goes to infinity, e to the minus x sine of x. The problem is sine of x. One thing you should remember is the limit of sine of x as x goes to infinity does not exist. It just oscillates forever. So here, for this limit, we get a 0 times does not exist. And that's an indeterminate form. It's not one that we can, that's one of our 7 that we just talked about that we use L'Hopital's rule for, but it is indeterminate. And actually, in this case, the trick is to use squeeze theorem. So, you know, our limit techniques are all, we can't forget our limit techniques, you know, plugging in, multiplying by the conjugate, trying to factor and simplify using squeeze theorem, and now L'Hopital's rule. So we can't forget now all of our limit techniques have to work together. So starting with sine of x being between -1 and 1, since e to the negative x is positive, I can just multiply through and then take a limit. And here, e to the minus x goes to 0 as x goes to infinity. Think about the graph. And so minus e to the minus x also goes to 0 as x goes to infinity. So the functions on the ends here, the limits of the functions on the ends here both go to 0. So by squeeze theorem, the limit of e to the minus x of sine of x as x goes to infinity must equal 0. So here is the summary of techniques for the indeterminate forms regarding L'Hopital's rule. So hopefully this will now make a little more sense. For 0 over 0 and infinity over infinity, we can use L'Hopital's rule directly. Nothing to do. For 0 times infinity, we write the product as a quotient, divide one of the terms by the reciprocal of the other. For infinity to the 0, 0 to the 0, or 1 to the infinity type, we rewrite the thing we're taking the limit of. We use the fact that a equals e to the ln of a, and then use properties of the log. Finally, for infinity minus infinity, there are many strategies involved, like combining the fractions, multiplying by the conjugate, factoring and canceling, you know, so that you kind of have to approach on a case-by-case basis. So that's L'Hopital's rule, very important. And this ends the lecture on L'Hopital's rule. Thank you so much. And thank you so much for signing up for my class, and take care, everybody.